Welcome everyone to the online training, module 3, but now we'll focus on lesson 2. Lesson 2 is about sampling and sampling techniques. And we'll look at the concept of sampling and then sampling techniques. Specifically, we'll focus on probability sampling techniques and non-probability sampling techniques. Before we look at sampling, it is important for us to note the distinction between a sample and population. What is a population? Population refers to all members that meet a certain set of specifications or a specified criterion. We can look at the population of the government or the state of the Gambia as comprising all the members that live within the geographic boundaries of the state of the Gambia. But a member or an individual member of a population is called an element. Now, in that population, when we only consider some elements, then those elements considered or selected form what we call a sample. In other words, a sample is a subset of a population, or a sample is a small proportion or portion of the population. And this sample is determined through the process known as sampling. But when all elements of a population are included in a study, such as an impact evaluation study, then that is a census, typically known in exercises that involve population and housing censuses, because every individual or element of a population is considered or included in that exercise. Now, what is sampling? Sampling is the process or technique of selecting suitable sample for the purpose of determining parameters of the entire population. In other words, sampling is the process that helps evaluators select or determine a sample which has the characteristics that can be used to determine the characteristics of the entire population. To conduct an impact evaluation study, evaluators therefore must consider some key aspects, which are: number one, what size the sample should be. What is the appropriate sample size, for example? 2, whether the sample size is statistically justified or not. And then, what method of sampling should be used? This is very important because, as we'll see shortly, there are different sampling techniques, and these are used in different circumstances. or based on different assumptions and circumstances. However, what is more important is that any sample must be representative. What does that mean? It means whatever sample that has been determined must represent the population from where it has been drawn or selected. This is particularly important where the researcher's interest is that the findings from that sample should be generalized to the entire population. Now let's look at sampling techniques. Generally, sampling techniques are categorized into two. First, probability sample or probability sampling technique. Under this technique, every element of the population has an equal chance of being selected. The other one is non-probability sample or sampling technique, where selection of elements or participants is based on the evaluators or researchers' personal judgment. So as you might already been thinking, what's the difference between the two? So in the first one, probability sampling, there is equal probability or chance of being included in a sample across the elements. Whereas in non-probability sampling, equal chance is not guaranteed. Before sampling, it is important that first evaluators define the population of interest. What is our population where the impact evaluation study will be conducted? Once that is done, then evaluators can construct a complete list of all the elements of that population from which the sample will be drawn. Now, the list of elements of a population can be taken from different sources. However, researchers or evaluators can use alternatives, particularly when logistics and expense of constructing a fresh list of the entire population is very high or too great. In other words, instead of constructing a new list going into a particular population where the evaluation will be conducted and start listing down the names of all the beneficiaries in that village or community or district or region, which might involve high cost or expenses of doing that exercise, evaluators can consider alternatives. Maybe there's already an existing list of beneficiaries or participants or members of that population. However, in doing so, caution must be exercised by the evaluators, especially when using an already constructed list of population members. What is important is that While doing so, evaluators must ensure that the list they are using is recent and exhaustive enough. The third step is drawing a sample. That means once the list of the elements or the elements in a population has been developed or constructed, evaluators must select a sample from that list. How is that done? One way is use of tables of random numbers. There are a number of random number tables that can be used to draw a population, rather a sample from a population. The fourth step is contacting all the members of that sample that has been drawn. Sometimes, and practically possible, it becomes difficult to contact every member or element that has been included in a sample. This could be due to geographical challenges, due to the fact that some members have moved out of a particular geographical area, or they have died altogether. Now, it's important for evaluators to note that failing to contact all individuals in the sample can be a problem. And somehow, the representativeness of the sample can be lost at this point. Let's look at an example to make this point more clear. Suppose a sample of 100 was randomly drawn from a population of 1,000 elements. Let's say these elements are the farmers. A survey questionnaire was sent to all the 100 sampled elements or farmers, and only 80 were completed and sent back the questionnaires. That means 20% of the questionnaires did not come back from the farmers. Here's a problem. Is the sample of 80 farmers, in this case, who participated, representative? Now, do they represent the population? Since 20% of the sample was not located, does it underrepresent some views? In short, can we generalize from our sample of 80 farmers, from the findings of 80 farmers, to the entire population of farmers? The representative sample in this case was 100, but only 80 have been corrected. So what is the remedy? This is a very common practical challenge, and different solutions are provided. One way is to say, well, let's just find a new set of 20 farmers and represent those who were not located. That seems very simple and easy to do, but the implications can be serious. Are the new 20 farmers that have been taken to replace those 20 who were not located the same? They could be different farmers. And that itself can introduce bias into the sample. The other solution is to say, well, let's proceed with our analysis based on the 80 farmers and indicate the limitations on how the findings can be applied. So a statement can be included that the findings are applicable to the 80 farmers who were, or the community from where the farmers were drawn, but not the entire population, so that the reader or whoever uses that information understands that limitation and knows the context within which to apply the findings of that study. Having looked at that, let's move on to probability sampling techniques. We may recall that probability sampling is also referred to random sampling or representative sampling. Why representative? Because the characteristics of a properly drawn sample represent the parent population from which it was drawn in all ways. And there are different techniques under probability sampling. Number one, there is simple random sampling, then stratified random sampling, then systematic sampling, and cluster sampling. So our discussion will focus on this. Simple random sampling. Under simple random sampling, each element in the entire population has an equal chance or probability of being included in the sample. So all elements have equal chance. The implication is that no one element is highly likely to be included than another. And this applies particularly to sampling without replacement. Why? Because under sampling with replacement, which is less used or used less frequently in impact evaluation studies, particularly because if we replace any element that we have sampled, there are high chances that the same element will be drawn several times, and that can affect our evaluation and the findings and conclusions, the recommendations drawn from such a study. So the implications of random sampling are that all choices are independent of one another. Choice of one element does not depend on choice of another element. Two, it gives each possible sample combination an equal probability of being chosen. All choices are independent as indicated earlier. Stratified random sampling. Under this technique, the population is divided into several subpopulations that are individually more homogeneous or more uniform than the total population, and then select items from each stratum to constitute a sample. Now, that process of dividing the population into several small subpopulations is known as stratification. And this stratification process is done based on several factors. This could be position or rank or income, could be education, sex, and any other factors of interest that would make these groups more homogeneous in a particular strata. Since each stratum is more homogeneous than the total population, Stratified sampling helps to generate more precise estimates for each stratum. Participants or elements are chosen randomly from each stratum. And because of that, it means a complete list of the population within each stratum must be constructed. Stratified samples are generally more accurate in representing the population than simple random samples. Why? Because elements are drawn from homogeneous stratum than random sampling, which is drawn randomly. They also require more effort than simple random sampling. Then let's move on to systematic sampling. Systematic sampling involves selection of every ith item on a given list. That means an element of randomness is introduced by using random numbers to pick the first element or unit. So the first unit is picked randomly by using random numbers. Thereafter, every ith item is selected until the sample is completed. Thus, in systematic sampling, only the first element is selected randomly. The rest are selected at fixed intervals. For example, if a 4% sample is desired, the first item would be selected randomly from the first 25. And thereafter, every 25th item will be included in the sample. Now, to do this in practice, it requires that a complete list of the elements of a population should be available. And they should be of considerable length. It's also important for evaluators to note one danger in using systematic sampling. Think of this. If there is a hidden periodicity in the population, when the system generates certain outcome periodically, the same element or the same product comes up at periodic intervals. In such cases, systematic sampling can be an inefficient method of sampling. For instance, every 25th item produced by a certain production process is defective. If we are to select 4% sample of the items of this process using systematic sampling, it means we would either get all defective items or all good items in our sample, depending upon the random starting position. Then let's move on to cluster sampling. Under cluster sampling, the population is divided into clusters. Then randomly select among these clusters to form a sample consisting of all or some units from these clusters. clusters must be characterized by heterogeneity between them or between one cluster and another, but there must be homogeneity within the cluster. In other words, the elements within each cluster must be homogeneous or display some element of uniformity. Cluster sampling can be done at 2 stages or at more than 2 stages, which is known as multi-stage cluster sampling. So if only 2 stages are involved, for example, divide the population into clusters and then draw a sample of clusters and select elements from those clusters. This is 2-stage cluster sampling. But if more than 2 stages are involved, that becomes multi-stage cluster sampling. An important advantage of cluster sampling is that it reduces cost by concentrating the survey, the evaluation, in selected clusters, leaving out others, instead of considering all clusters. You just select a few, and evaluation is based on that. But in doing so, cluster sampling becomes less precise than random sampling. Let's move on from probability sampling to non-probability sampling techniques. Under non-probability sampling techniques, researchers purposively choose particular units of the universe for constituting a sample. That means the judgment of the evaluators or researchers play a key role or part in the sampling design. And there are several techniques under non-probability sampling, which include convenience sampling, purposive sampling, QUOTA sampling, snowball sampling, and many others. But for the purpose of this discussion, we'll focus on these. Convenience sampling. This technique involves selecting participants because they are often readily and easily available to the researcher. So this technique helps researchers to overcome many of the limitations associated with research. For example, convenience sampling can involve using friends, people that the evaluators are already familiar with. Could be family members as part of the sample, which is easier than targeting unknown individuals or strangers. Convenience sampling, however, is least reliable design, yet it is the cheapest and easiest to conduct. Then we move on to purposive sampling. Under purposive sampling technique, the subjects or elements are selected for a specific characteristic or quality and eliminates those who fail to meet these criteria. However, there is no assurance that every element or subject has some specifiable chance or probability of being selected. Then we move on to QUOTA sampling. Here, the subjects are selected based on some predetermined characteristics to meet a predetermined or known percentage. Selection of a sample that is similar to the population in terms of proportion of certain characteristics. So this can be based on gender. So evaluators might be interested in making sure that all genders are included in a population. So females, males, and also maybe other groups like the youth, the elderly, and other groups as defined based on specific characteristics to meet certain proportions of the sample. The actual selection of the items for the sample is left to the interviewer's discretion. And as you can see, it is very convenient and relatively less expensive. Let's look at snowball, also known as network or chain sampling. Under this technique, selection usually is done by using networks. It is useful when the researcher knows little about a group or organization to study. So what do evaluators do? They will contact with few individuals, and those individuals will direct the evaluators to the next individuals or next groups, and so on until the sample is met. So this technique will be difficult to use when the sample becomes larger and larger. It works when the sample is small, and it is also mostly applicable in small populations that are difficult to access due to their closed natures, depending on the nature of the study or the evaluation study. Now, having looked at both probability and non-probability sampling, let us now look at some errors that are common while we are doing sampling. These errors are generally categorized into two: systematic sampling error and random sampling error. Systematic error occurs when the sample is not drawn properly for various reasons. It can also occur if names are dropped from the sample list because some individuals or members were difficult to locate or uncooperative. So in such cases, the evaluators may just consider replacing those. And as we said earlier, that can introduce an element of bias into the sample, and the sample ceases to be representative. It can also occur when individuals dropped from the sample could be different from those retained, as indicated earlier. On the other hand, random sampling, also known as chance error, occurs when samples drawn from the same population will rarely provide identical estimates of the population parameters of interest. So suppose we draw 2 or 3 or more samples from the same population. The estimates that we get from those samples will vary from sample to sample. This is known as chance error. That variation in the estimates between one sample and the other drawn from the same population is known as chance error. Now, researchers decide the amount of error they are willing to tolerate and the level of confidence they want to have. And commonly, this margin of error is expressed in terms of confidence interval. For example, 95% confidence that If other evaluators were to conduct the same research, they would get similar estimates or findings. Thank you for your attention.